Astronomers recently pointed the most powerful space telescope ever built at a distant world hundreds of light years away. They expected darkness, maybe faint reflected starlight. Instead, the planet was glowing. Not flickering or reflecting, but glowing on its own. And right now, scientists still don't fully understand why.
It wasn't supposed to shine like that. When astronomers aimed the most powerful space telescope ever built at a distant world, they expected faint reflected starlight, maybe a subtle atmospheric signature. Instead, they saw something startling. The planet was glowing. Not reflecting, not flickering, glowing on its own. And right now, scientists are still trying to figure out why. The discovery came from observations made by the James Webb Space Telescope, the most sensitive infrared observatory ever sent into space. Unlike older telescopes that primarily detect visible light, Webb sees heat. It detects thermal radiation. It can measure subtle changes in atmospheric chemistry on worlds hundreds of light years away. But this signal wasn't subtle. The exoplanet, cataloged in a distant star system, appeared brighter in infrared wavelengths than models predicted. Much brighter. In fact, after accounting for its distance from its host star, its size, and expected atmospheric absorption, the planet should have been relatively dim. Instead, it looked like it was generating extra energy. Exoplanets glow for simple reasons. Young planets retain heat from their formation. Gas giants radiate internal heat as they slowly contract under gravity. Tidal forces can stretch and compress a planet, generating friction and warmth, similar to what happens on Jupiter's volcanic moon Io. But this case doesn't fit neatly into those explanations. The planet is not young enough to retain intense formation heat. It is not close enough to its star to be roasting under extreme radiation like hot Jupiters, such as WASP 12b. And current models of tidal heating don't fully explain the excess infrared emission being observed. So what's going on? Let's break it down. When Webb observes an exoplanet, it often uses a technique called transit spectroscopy. As the planet passes in front of its star, some starlight filters through the planet's atmosphere. By analyzing how that light changes, scientists can determine atmospheric composition, water vapor, methane, carbon dioxide. But Webb can also observe planets when they pass behind their stars. That allows astronomers to subtract the star's light and isolate the planet's own thermal glow. That's when the anomaly appeared. The planet's dayside temperature was far higher than predicted. And more intriguingly, the glow didn't fade in a way that matches typical cooling patterns. It was persistent, stable, structured. Now, glowing planets aren't unheard of. The exoplanet 55 Cancri E, for example, has shown dramatic temperature swings, likely due to volcanic activity or a lava ocean. Similarly, HD 189733b has displayed intense atmospheric storms and dynamic heat distribution. But in those cases, the energy output still fits within astrophysical expectations. This new planet doesn't. One possibility is atmospheric chemistry behaving in unexpected ways. Certain molecules can trap heat efficiently. If the atmosphere contains exotic compounds, perhaps metal oxides or unusual hydrocarbons, it might act like an extreme greenhouse system, retaining far more heat than models assume. Another hypothesis involves internal activity. If the planet has a molten core undergoing intense convection, or if it experiences tidal stretching from a hidden companion body, it could generate additional internal heat. In our own solar system, tidal heating transforms icy moons into geologically active worlds. Io glows with volcanic hotspots because of gravitational interactions with Jupiter. Europa likely harbors a subsurface ocean kept warm by similar forces. Could something similar be happening here, but on a planetary scale? It's possible. Yet some details complicate the picture. The glow's spectral fingerprint doesn't match typical volcanic gases. It doesn't show the obvious signs of magma oceans. And its brightness distribution suggests uniform heating rather than isolated hotspots. That's strange, because planets are rarely uniform. Another angle scientists are exploring involves magnetic interactions. If the planet has a powerful magnetic field interacting with stellar winds from its host star, that interaction could inject energy into the atmosphere. Similar processes occur with Earth's auroras. though on a much smaller scale. Imagine an aurora so powerful it heats an entire hemisphere, circulation gone extreme. On tidally locked planets, where one side always faces the star, winds can transport heat across the surface in dramatic ways. Some hot Jupiters exhibit supersonic winds that redistribute energy globally. If this exoplanet's atmospheric dynamics are unusually efficient, they could create the illusion of excess energy. But again, the numbers are off. The brightness exceeds circulation-based predictions. So researchers have started considering more exotic physics. Could we be miscalculating the planet's albedo, the amount of light it reflects? Could high-altitude clouds be amplifying infrared emissions? Or are we seeing non-equilibrium chemistry, where chemical reactions release heat continuously? JWST's instruments are incredibly precise, but they're also revealing how incomplete our models are. For decades, exoplanet science relied on indirect data. Now we are directly measuring atmospheric properties with unprecedented clarity. And clarity sometimes exposes confusion. The glow also challenges assumptions about planetary aging. Traditionally, planets cool as they age. Heat dissipates. The universe is not obligated to make sense on the first try. It reveals itself slowly, through signals, through spectra, through unexpected brightness curves that force us to pause and rethink what we thought we knew. Each new observation peels back another layer of mystery, showing that planetary behavior is far more varied and intricate than textbooks have long suggested. Patterns emerge and dissolve, hinting at processes we cannot yet fully simulate. Chemical reactions in the upper atmosphere that defy expectations, heat flows from deep interiors that models underestimate, or perhaps entirely new forms of energy transport that only reveal themselves under extreme conditions. The planet, in its quiet brilliance, demands patience and careful measurement, reminding us that the universe often communicates in subtleties rather than proclamations. The data from JWST is precise enough to challenge decades of assumptions, forcing astronomers to confront the possibility that some planets operate under rules we have not yet imagined. In this sense, the glow is more than a curiosity. It is a teacher, a portal into the hidden mechanics of distant worlds. It challenges astronomers to question assumptions about planetary evolution, to refine models of heat distribution, and to reconsider how magnetic fields, winds, and chemistry might interact on scales far beyond Earth's experience. Observing it is an exercise in humility. No matter how sophisticated our instruments, the cosmos retains surprises. And yet, each puzzle carries promise. By decoding this persistent light, scientists gain insights not only into a single distant world, but into the fundamental physics that govern planets everywhere. The glow could be a signature of exotic internal processes, unseen atmospheric dynamics, or interactions with a hidden companion object, or perhaps a combination of all three. Every hypothesis tested, every simulation run, and every spectrum analyzed contributes to a broader understanding of planetary systems as dynamic, evolving entities. It reminds us that exploration is never just about collecting data. It is about embracing uncertainty, learning to interpret signals that challenge preconceptions, and discovering patterns that expand the boundaries of our knowledge. In this way, the exoplanet's unexpected brightness is a beacon, illuminating not just a distant world, but the path forward for planetary science, where every anomaly deepens our appreciation for the complexity and wonder of the universe. This exoplanet is glowing, not metaphorically, not poetically, physically, and until scientists unravel the mechanism behind that glow, it stands as a reminder of something fundamental. We are still at the beginning of understanding the worlds beyond our own, and the more we look, the stranger they become.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.